Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's activity is experimental verification of Ohm's Law. Our objective today is to verify Ohm's Law using real-world components and instrumentation. Additionally, we'll discuss basic troubleshooting scenarios. Finally, we'll plot current and power as a function of applied voltage for different resistors. This activity will tie together a number of topics, including fixed and variable resistors, the resistor color code, Ohm's Law, the power equations, ohm meters, voltmeters, power supplies, and ammeters. If you've been following this playlist in its intended sequence, or if you're intimately familiar with these topics, no worries. If not, I definitely recommend hitting these prerequisite lectures available at the Big Bad Tech channel prior to continuing. This activity is especially exciting for me because, again, it represents the synthesis of a number of previously unrelated topics, and additionally represents a perfect opportunity to ambush you with some especially harsh reality checks. Be warned. First, we're going to do a couple permutations of Ohm's Law and the power equations, then we'll discuss common troubleshooting events for basic labs, and finally, we'll bring it on home with a quick lab activity that plots current and power as a function of applied voltage for two different resistors. I'm encouraging you to get involved with this activity and pause the lecture often to perform the required calculations. If you get lost, I'll be right there to guide you through the correct solutions. This exercise should be especially satisfying because using limited observations and electrical theory, you can predict reality. That's the point. Real electrical properties and components, with some margin of error, really do work like I've been telling you they do. I am not a dim-witted peddler of nonsense, and today I will prove it to you. Our first task is a very simple verification of basic Ohm's Law properties using lab instrumentation. We're going to build the following circuit. It's a 20-volt source supplying current to a resistor with a 4-band color code of yellow, purple, black, gold. Pause the lecture and see if you can determine the current through and the power dissipated by this resistor for this configuration. We'll use the ohm meter to check the actual resistance of the resistor, and we find it's 0.0464 kiloohms, or 46.4 ohms. Very close to the anticipated value of 47 ohms as indicated by the 4-band color code. We'll set up its power supply and verify its output with a voltmeter. 20.06 volts is close enough. Now we'll build the circuit and see if our observed current matches that of your expected calculations. You did do the calculations, didn't you? In this case, I'm coming out of the power supply and going into an ammeter, out of the ammeter into my resistor on the protoboard, and then back to my power supply. So far, so good. But the moment I turn on the power supply, things start going south. What's going on here? Not only is my power supply reading the incorrect current of roughly 343.5 milliamperes, in case you haven't noticed, my circuit is on fire. This is to be generally avoided. Ambush, right out of the gates. Did I not warn you I was going to do this? Did you pause the lecture and do the calculations like I asked you to? If you did, you should have seen the following figures. When a 47 ohm resistor is hooked up to a 20 volt DC source, current equals voltage divided by resistance. 20 volts divided by 47 ohms induces approximately 425.5 milliamperes of current. When 425.5 milliamperes of current is flowing through a 47 ohm resistor with 20 volts across it, we realize any permutation of the power equations yields roughly 8.5 watts of power dissipated by this resistor. Now, using these figures of 425.5 milliamperes and 8.5 watts, can you figure out why we're observing these two symptoms? Number one, why do we only observe 343.5 milliamperes and not the 425.5 milliamperes as we calculated? And number two, most importantly, why is our circuit on fire? Pause the lecture and think about this. Why is our current limited? And why is it on fire? Realize I am not limiting you on resources. I'm encouraging you to look back at your notes and make use of your previous understanding of power supplies, Ohm's Law, power equations and basic components like fixed resistors. Rewind the video clip if you want to, because there might be some additional clues you overlooked the first time you saw it. If you've been following these lectures in their intended sequence, I have stuffed your bag full of tricks, and it's now your job to rummage through that bag and use those tricks to interpret reality. In answer to our first question, why is the current limited to 343.5 milliamperes and not the 425.5 milliamperes we'd expect to observe? Realize power supplies have practical limitations regarding the amount of current and power they can supply to a circuit. The 10 triple output power supply is limited to a maximum of 500 milliamperes of current, and this maximum current is capable of being reduced using the current control knobs associated with the adjustable outputs. In this case, the current maximum just happened to be set at 343.5 milliamperes when we hooked up our 47 ohm resistor to a 20 volt circuit. As soon as we turn on the power supply, it pegs out at this limit. The dead giveaway to this is the LED on the output indicates this set of terminals is in constant current mode. The voltage output isn't 20 volts as we had expected, but rather around 16 volts as indicated on the needle meter. This is the voltage necessary to produce our current limit of 343.5 milliamperes through a 46.4 ohm resistor. Because the supply is in constant current mode, it reduces the voltage to approximately 15.9 volts. Only if the current limit was at or above 425.5 milliamperes would the power supply function in constant voltage mode. The point of this harsh reality check is that real-world power supplies have performance limits and user-adjustable settings inside which you must operate. In answer to our second question, why is this resistor on fire? Look at it. It's a tiny, itty-bitty little pipsqueak of a resistor. If you did what I initially asked and did the current and power calculations prior to starting the experiment, you'd realize that we'd ordinarily expect a 47 ohm resistor to draw 425.5 milliamperes from a 20 volt source. Using any permutation of the power equation, you'd realize that the supply would be delivering and the resistor would be dissipating 8.5 watts of power. This is not an 8.5 watt resistor. A resistor of this size and power rating is instantly going to go up into smoke the moment it was exposed to these conditions. The only reason it took a couple seconds to go up into smoke is that the power supply is current limited to 343.5 milliamperes. In these conditions, the power dissipated by this resistor is power equals I squared R, 343.5 milliamperes squared, times 46.4 ohms, yields approximately 5.5 watts, which is still obviously way too much for this tiny resistor to handle. The point of this harsh reality check is that real-world components like resistors have power dissipation and performance limits inside which you must operate, otherwise they can be irrevocably and dangerously destroyed. The point of this ambush is to wave a lit torch in your face and get you to snap out of it. Do the calculations first. Don't be a zombie and sleepwalk through a lab or a maintenance procedure and not pay attention to the numbers. You are going to get yourself killed, or at the very least damage equipment if you don't know what you're getting yourself into, nor paying attention to the numbers. You cannot see moving electrons, but when an excessively large quantity of them is rapidly turning your circuit into smoke, its effects are readily apparent. Your DMM is an extension of your senses. Use it as such. Only by understanding the concepts behind these numbers are you capable of interpreting observations in reality. Alright, now that I've got your attention, let's do a couple basic permutations of Ohm's Law before we introduce basic troubleshooting or start graphing data. I promise I'm not going to ambush you this time, but I still want you in a state of cat-like alertness, ready to pounce at a moment's notice. Get involved and do the calculations first. Know what is behind the door before you open it, because you never know. Let's use a variable resistor to demonstrate all three basic permutations of Ohm's Law and talk about good lab practices. A potentiometer, if we recall from the variable resistor lecture, available at the Big Bad Tech channel, is a 3-terminal device with a fixed resistance between the two N terminals, A and C, and an adjustable B terminal that slides the length of the A to C path. Simply by varying the position of the B terminal we can adjust the resistance from A to B or B to C, where RAB plus RBC is always equal to the fixed value RAC. In this case, let's use a 1 kilo ohm potentiometer and our DMM in ohm meter mode to establish 500 ohms of resistance between any two terminals. First, we'll use the ohm meter to establish which of the three terminals is A, B, and C. In this case, I'm observing a constant value of 1041.3 ohms of resistance, regardless of the position of the adjustable screw. These are the A and C terminals. Now I'll just move one of my leads to the B terminal and adjust the potentiometer to 500 ohms. Look at that, right on the money. You can't get much more perfect than that. Now just remember between which two terminals this 500 ohms appears. The other 541.3 ohms of this 1041.3 ohm potentiometer is on the other side. If we use that side instead of the one we meant, our answers would be close but suspiciously off just enough to warrant further inspection. Now pause the lecture and see if you can use Ohm's Law to determine the expected current draw by a 500 ohm resistor when it is supplied by a 12 volt source. Additionally, make sure our expected power dissipation is below, let's say, a half a watt. Ohm's Law states that current is equal to voltage divided by resistance, 12 volts divided by 500 ohms. We'd expect to observe 24 milliamperes of current. If power is equal to voltage times current, 12 volts times 24 milliamperes yields 288 milliwatts, well inside our desired power dissipation rating. Now, well armed with expectations, we are not just bebopping into an ambush. Can our power supply provide 24 milliamperes of current? Yeah, no problem. All we got to do is make sure our current limit is set above this though, or it'll just max out at whatever limit you've got it set at. Next question, can our component handle it? Yeah, I told you to keep it below a half watt and we are. Let's fire it up. Let's set up our power supply to provide 12 volts. Start off using the analog needle meters. It looks like it's reasonably close to 12 volts, but I'm going to use my DMM in voltmeter mode just to make sure. The DMM says I'm actually under the mark at close to 11.1 volts. Now, keeping the DMM in voltmeter mode attached, I can adjust the power supply closer to 12 volts. Notice my potentiometer is on my protoboard, but I've not yet attached the power supply to the protoboard. What I'm measuring here is the output voltage of the power supply in an unloaded condition. Unloaded means there is an open circuit at the power supply's output and it is not supplying current, because I'm obviously not connected to the potentiometer. In a perfect world, a power supply output voltage won't deviate from its unloaded condition compared to when it's loaded or supplying current. We don't live in a perfect world. We live in the real world, and we can therefore anticipate variations in output voltage for various output conditions. I'll explain why power supplies exhibit this behavior in later series DC circuit lectures. With our 500 ohm resistor attached to our power supply, our DMM in voltmeter mode shows the output voltage drops to around 11.5 volts. Again, keeping the DMM in voltmeter mode, I can readjust our output power supply back up to the 12 volts we require when in loaded conditions. It may seem like a pain, but realize I've measured and adjusted the output voltage several times. Once using the analog needle meters on the front of the power supply, a second time using the DMM in an unloaded condition, and a final third measurement using the DMM in voltmeter mode when the circuit is in a loaded condition. The purpose of this successive bracketing is to make sure we're reasonably close to 12 volts when we start and exactly at 12 volts when we're making measurements. This ensures that there's no damage to our equipment and we really are operating at known conditions. If we were to assume from either our initial analog needle meter measurement or our unloaded voltage measurement, we would not have been operating at 12 volts. With the wrong voltage supplied, our measured value of current would be wrong. Reality follows the GIGO principle. Garbage in, garbage out. Now, power off. Modify the circuit to incorporate an ammeter in series with our circuit. Out of the power supply, into the ammeter, out of the ammeter, into the B terminal of our potentiometer, out of the A terminal of our potentiometer back to our power supply. Power back on, we're seeing 23.73 milliamperes of current through our resistor, extremely close to our expected value of 24 milliamperes. At least for this operating conditions, Ohm's law is true. Notice we juggled the DMM and ohm meter, voltmeter, and ammeter mode. And at no time were we ever unaware of our operating conditions, nor did we ever set anything on fire. This is the minimum standard of success. Don't break things. I know this seems overwhelming and confusing now, but with repeated exposure to this equipment, this will get easier and easier. Get involved in a hardware lab and get in the driver's seat. Do not let your lab partner dominate the bench. You need just as much exposure to this equipment as they do, and chances are you're probably not going to set things on fire like they will. Let's continue our repeated exposure to Ohm's law with a variation on the same theme. What if I was to keep the resistance constant at 500 ohms and randomly spin the output voltage knob until the ammeter read 40.01 milliamperes? What is the voltage drop across this resistor? Notice I covered up the analog needle meter to prevent you from cheating. Not that that would help, because we've already demonstrated these meters are a lot like your lab partner, hopelessly inaccurate. Pause the lecture and see if you can determine the voltage drop across a 500 ohm resistor with 40.01 milliamperes going through it. A reconfiguration of Ohm's law states that voltage is equal to current times resistance. 40.01 milliamperes times 500 ohms yields approximately 20 volts. Power off, remove the ammeter, and insert a voltmeter. We find the observed voltage value of 20.27 volts is extremely close to our expected value. Ohm's law again holds true. Now, keeping the applied voltage at 20.27 volts, let's try another variation of Ohm's law. I'm going to remove the voltmeter and reinsert an ammeter, and then just randomly spin the adjustment screw on the potentiometer until the current draw is 30.04 milliamperes. I'll recheck the voltage just to make sure this loaded condition is still at 20.27 volts, and it is. What did I do to the resistance if the voltage stayed the same and current dropped? Think about it before you answer. No numbers. Voltage stayed the same. Current dropped. Did I increase the opposition or did I decrease the opposition? If you said anything other than increase resistance, you need to stop and go back to the Ohm's Law lecture, available at the Big Bad Tech channel, and perform some serious review. Again, at minimum, you simply must understand that if resistance increases, current goes down. If resistance decreases, current goes up. No numbers necessary. You must understand this basic give and take relationship. Now, let's just put some numbers in there. What's the resistance that draws 30 milliamperes of current with approximately 20.3 volts across it? Ohm's law states that resistance is equal to voltage divided by current. 20.27 volts divided by 30.04 milliamperes yields approximately 674.8 ohms of resistance. When we remove the potentiometer from the circuit and check the resistance between the two terminals we used, our ohm meter states we're extremely close to this value at 669 ohms. You at this time should be absolutely convinced that Ohm's law is not just purposeless busy work, but a real and observable property of electrical circuits that can be readily applied to circuit analysis. Now let's discuss basic troubleshooting scenarios. Your first lab is not going to go this smooth, and you're going to fumble something, and provided you make the recovery and don't set anything on fire or damage equipment in the process, that's okay. That's the point of a hardware lab. Make all the mistakes now in a safe and supportive environment and learn from them. Recognize faults and be sufficiently aware enough to prevent their reoccurrence. Let's introduce some basic errors in our circuit. There's only one element, so the troubleshooting opportunities are pretty limited. But you'd be surprised how often these scenarios occur in early labs. We'll introduce open circuits, short circuits, and other scenarios induced by incorrect placement of components, wires, and instrumentation. Opens. Like I've previously said, the open circuit is the troubleshooting scenario you'll most likely encounter. regardless of its source, whether it's an errant open switch, a disconnected wire, or an improperly placed instrument. An open circuit will not allow current flow. If there is no current flow through an element, there will be no voltage drop across an element. This being said, if the source is on, there will still be a voltage drop somewhere in our circuit because there is a voltage rise, and therefore there must be an associated voltage drop. If there is one and only one open in our circuit, the voltage drop occurs at that open. Here's a close-up of the return wire removed from our circuit with the ammeter inserted. Remember, protoboards are temporary circuit building environments, and just by accidentally wiggling this wire, it could pop out of the connection point. Be gentle and handle appropriately. With this single wire removed, the current indicated by our ammeter instantly drops to 0 milliamperes because a complete circuit no longer exists. Now is the time to get up close and personal with this protoboard. Scan it and see if you can find a wire just dangling out in space. Don't think it's going to be this obvious though. Most likely it'll just be subtly out of place and it'll be up to your attention to detail to notice this. Look at your circuit from different angles. Notice my first step towards resolution of this open had nothing to do with panic, nor additional instrumentation. My first step towards resolving this troubleshooting scenario is to simply observe. Use your senses. Look, listen, feel, smell. Generally, we try to avoid tasting circuits though. Look. Visual inspection will indicate dangling wires, or in other troubleshooting scenarios, burn marks, mechanical wear, or leaks. A pool of oil usually collects below the leak. Listen. An improperly aligned gearbox, faulty bearings, a stalled motor, or the loss of a single phase in a 3-phase AC motor have uniquely identifiable sounds. Feel. Components subjected to unusually high electrical current, like a stalled motor or an unusually high pressure drop without accomplishing work in a hydraulic system, will be unusually warm. It goes without saying that power should be off and you need to take necessary precautions when you feel these components. Smell. Finally, it sounds strange, but the first thing you do when you walk into a troubleshooting scenario is smell the air. The resistor I ignited at the beginning of this activity has a uniquely identifiable smell. If you smell that smell, the problem is electrical in nature. Oil subjected to intense heat undergoes thermal degradation and changes odor. Know the difference. Fresh oil should smell sweet. Thermally degraded oil smells like a campfire. Troubleshooting is not magic. It's just good observation skills paired with reasoning. Beyond the ranges of your senses is when you need to resort to instrumentation. If we could not see these wires, but only had access to certain test points within our circuit, we'd have to progressively trace through our circuit and perform voltage checks at certain points. If we had a common frame of reference like ground, we could use this to our advantage or just choose one for this purpose. Using a voltmeter on a circuit would mean nothing if we didn't know what to expect. Again, that's the point of calculations. They establish expectations against which we can compare reality. Ordinarily, the only voltage drop with a single element in a circuit would be observed across that single element. However, progressively working through the circuit with an open between the resistor and the negative lead of our voltage source, we'd observe the voltage drop at the open. Additionally, opens can be created not just by errant wiring, but also improper placement of instrumentation. Consider a voltmeter not placed across or in parallel with something, but rather through or in series with something. Voltmeters don't go in series. Voltmeters are modeled as extremely high resistances. And if we assume this modeled high resistance is an open, no current can flow through a voltmeter. Current stops. Yes, where you improperly place the voltmeter, there is a voltage drop. However, there is no current flow through an open. Shorts. Consider the opposite scenario, a case where too much current is observed. This is a short. Again, a short is the errant placement of a low resistance path in our circuit. If the resistance is too low, current will be too high. Shorts could be caused by a couple reasons, like improper placement of an ammeter, improper placement of a component, or even a stray wire making contact with something it shouldn't. Extra wires don't get you extra points. They just make it extra hard to troubleshoot faulty circuits. Consider improper placement of an ammeter across the variable resistor. Ammeters never go across components. They're always placed in series. Ammeters can be modeled as extremely low resistance paths. With an extremely low resistance path across or in parallel with our component, our total resistance seen by the source is extremely low, a substantial amount of current can flow. In this case, the power supply maxes out at the preset current limit. Notice the power supply indicates it's in constant current mode with the LED. This is a dead giveaway something is shorted out. I know the picture shows a blank screen on the ammeter, but it's actually flashing a string of 4 zeros, which indicates for a BK Precision DMM that the ammeter is over range. Remember, some DMMs must be manually ranged. If you're reading current above that range, the DMM says so. Again, do not interpret an overload or an overrange as an indication of no current. An overload or an overrange is just the opposite. There's too much current because of the short. If the ammeter was in the maximum range and provided it was still readable, we'd observe the current limit of our power supply. Consider another cause for identical symptoms of too much current. What if the potentiometer was installed in our protoboard incorrectly? If you know how protoboards work, it is immediately evident that the 3 leads of this potentiometer are all tied to the same node, because the 5 connection points in this row are all tied together via a conductive clip that is not visible to the naked eye. However, immediately recognizable to those that know how to use an ammeter and a protoboard. Again, you need to identify not only the proper terminals for the components you're using, you've got to deploy them in your circuit building environment correctly. A potentiometer inserted in this manner is shorted out and presents minimal resistance to our source. Even with the ammeter in the correct position, the power supply pegs at the current limit and the ammeter is in the overload condition. Other errors. If you observe errors other than the extremes of open or short circuits, this is where your knowledge of Ohm's law comes into play. If you observe current values other than you'd expect, consider verifying the source voltage and the resistance setting, or both. If there's too much current, you've either got the voltage set too high or the resistance set too low, or both. If there's too little current, you've either got the voltage set too low or the resistance set too high, or both. I'm intending to supply 12 volts to 2 terminals of a variable 1 kiloohm potentiometer set at 500 ohms. Ordinarily, I'd expect 24 milliamperes of current, but I'm only observing approximately half this current at 11.4 milliamperes. The power supply is at 12 volts. What's the problem? I'll tell you what the problem is. If voltage is correct and I'm observing half the current I'd expect, the resistance is twice as much. I'm using the potentiometer wrong. I'm hooked up A to C and observing all 1 kiloohms of resistance, regardless of the position of the adjustable B terminal. This goes to show you that you could have the perfect voltage and the perfect resistance and still screw it up by building the circuit wrong. Again, Ohm's law quickly and easily and directly routes me to the source of this problem. I don't mean to go all Sherlock Holmes on you, but skills like deductive and inductive reasoning are essential to becoming a good troubleshooter. Deductive reasoning is top-down logic, where a conclusion is reached by applying general rules that hold over the entirety of your domain of interest, properties like Ohm's law. Inductive reasoning is bottom-up logic, where the conclusion is reached by generalizing or extrapolating from initial observations. Numeric literacy and your familiarization with your DMM is essential for the interpretation of initial observations. When deductive and inductive reasonings crash headlong into each other, you've found the problem. Fix it. If the symptoms disappear, the case is closed. If the symptoms don't disappear, it's back to the drawing board. Troubleshooting might not be one shot, one kill, but only the most uninformed and stubborn of people let troubleshooting become a grueling battle of attrition. Your knowledge of basic properties like Ohm's law can cut out a majority of the labor. Truly half the time saved is simply the avoidance of checking and fixing things that aren't broken in the first place. Now that we've seen some basic permutations of Ohm's law and discussed basic troubleshooting scenarios, let's perform an experiment. Gather some data and plot the data on a graph. We're going to take two different resistors, a 470 ohm resistor and a 390 ohm resistor, and measure current through them when they're supplied by different voltages. Using our understanding of Ohm's law, we should be able to perform several hypotheses about the relationship of current as a function of voltage. Number one, given that the resistors aren't equal, the larger resistor should have less current, and the smaller resistor more current for the same operating voltage. 2. Additionally, we should expect for each resistor, if we increase the voltage, current should also increase. Long story short, both resistors should demonstrate linearity, where every increase in voltage shows an increase in current by the same proportionate amount. Given we're plotting the data for two different resistors, and our understanding of the first hypothesis, the smaller resistor should show a steeper slope, meaning current climbs faster, and the larger one a shallower slope, meaning current climbs slower. Additionally, we should be able to form a third hypothesis about power dissipation at various operating points. 3. Given current is an effect of applied voltage and power is the product of voltage and current, we should expect that power will not behave linearly, but rather geometrically as a function of applied voltage. The geometric nature can be demonstrated by doubling the applied voltage. If the voltage doubles, current should also double. Therefore, power, being the product of doubled voltage and doubled current, is quadruple our original operating point. Additionally, the two other permutations of the power equation make this geometric nature readily apparent by squaring either the applied voltage or observed current. Let's see if these hypotheses are true for these two resistors over a span of voltages. We're going to take our two resistors and simply measure current at different operating voltages. In this case, let's go 0 to 12 volts at 2 volt intervals. Every time we increase the voltage, we'll record the observed current on a data table. We'll then use the data table to plot the current for each resistor on the y-axis with voltage on the x-axis. We'll then calculate power as the product of voltage and current and graph that on the y-axis with voltage on the x-axis. Before we begin, we'll need several empty data tables, one of which will be used to fill out our expected values. Pause the lecture and see if you can use your understanding of Ohm's law and the power equations to fill out the expected current and power dissipation for both resistors at the following operating voltages: 0, 2, 4, 6, 8, 10, and 12 volts. There's the current for the 470 ohm resistor, the power for the 470 ohm resistor, the current for the 390 ohm resistor, and the power for the 390 ohm resistor. Again, do the calculations first. Have some idea of what's behind the door before you open it. Obviously, with 0 volts applied across a 470 ohm resistor, we should observe 0 amps of current through it, and it should be dissipating 0 watts of power. If the voltage was raised to 2 volts, we'd expect 2 volts divided by 470 ohms, or approximately 4.3 milliamperes of current. We'd expect this resistor to dissipate roughly 8.5 milliwatts of power. Now just walk through every possible combination of voltages for the 470 ohm resistor and calculate current and power. We do the same for the 390 ohm resistor at the same operating conditions. I know it seems repetitious busy work, but it's easy. Ready, aim, fire. Ready, aim, fire, using weapons you need practice with, notably Ohm's law and the power equations. For all practical purposes, you could just dump your expected conditions and formulas into a Microsoft Excel spreadsheet and get Clippy, Microsoft's annoying mascot from the late 1990s, to do the dirty work for you. While you're at it, Clippy, make me a graph of expected current as a function of voltage and power as a function of voltage. Actually, wait, that just spoiled the fun. Clippy, just make me a sandwich and let's do this lab. Walking through every possible combination of voltages for both resistors, we'd expect to observe the following conditions in the upper left-hand corner datasheet. Immediately below is a blank datasheet we'll use to record our observed values. First up, we need a 470 ohm resistor. What's a 4-band color code for a 470 ohm resistor? 4 is yellow, 7 is purple, brown means it's followed by 1 0. We'll use a plus or minus 5%, so the last band is gold. Yellow, purple, brown, gold. Go fetch. Our DMM in ohm meter mode says this one is actually a 466.3 ohm resistor. That's okay, it's inside the tolerance. But since this resistor is ever so slightly lower than 470 ohms, we should expect to observe current ever so slightly higher than our expected values. When there's 0 volts across it, there's obviously 0 amps of current through it, and it's dissipating 0 watts of power. Using our DMM in voltmeter mode, we dial the power supply close to our 2 volt operating point at 2.014 volts. Using our DMM in ammeter mode, we observe 4.214 milliamperes of current through it. Notice my leads are in a place different on the DMM when I'm using it in ammeter mode, and the ammeter is inserted in series with the resistor. Every time I switch between voltmeter mode and ammeter mode, I'm using the function, leads, range, and placement checklist. We enter this observed data in our data table and compare it with our expected values. 4.214 milliamperes is really close to 4.3 milliamperes. So far, so good. With a reasonable degree of accuracy, we're off to a good start. We could calculate power right now if we wanted to, but we could also just save that for later. I don't want this video lecture to get too long, so I'm going to kind of fly through these observed values and just go ahead and record them in your own data table. My observed in the lower left hand here is going to stay blank for a while. Using our DMM in voltmeter mode, we dial the power supply super close to our next operating point at 4.001 volts. Using our DMM in ammeter mode, we observe 8.368 milliamperes of current through it. Go ahead and enter this observed data in your data table and compare it with your expected value. Looking good. Using the DMM in voltmeter mode, we dial the power supply close to our next operating point at 6.030 volts. Using our DMM in ammeter mode, we observe 12.65 milliamperes of current through it. Enter this observed data in your data table and compare it with your expected value. Again, we're looking good. Using our DMM in voltmeter mode, we dial the power supply close to our next operating point at 8.057 volts. Using the DMM in ammeter mode, we observe 16.967 milliamperes of current through it. Enter this observed data in your data table and compare it with your expected value. Again, we're looking good. Using our DMM in voltmeter mode, we dial the power supply close to our next operating point at 10.053 volts. Using our DMM in ammeter mode, we observe 21.42 milliamperes of current through it. Because I'm using a manually arranged meter, notice I had to step up to the next available range, 200 milliamperes, to measure this current value. The 20 milliampere range wouldn't measure it. If this DMM was auto-ranging, I wouldn't have to take this step. Go ahead and enter this observed data in your data table and compare it with your expected value. Looking good. Finally, using our DMM in voltmeter mode, we dial the power supply close to our last operating point at 12.038 volts. Notice again, since our meter is manually arranged, I need to step back down to the 20 volt range to measure this accurately. Using our DMM in ammeter mode, we observe 25.67 milliamperes of current through it. Again, because I'm using a manually arranged meter, I had to step up to the 200 milliampere range to measure this current value, since the 20 milliampere range wouldn't measure it. Enter this observed value in your data table and compare it with your expected value. Looking good. Now let's take a break and chat about what we observed. Notice by continually employing the function, leads, range, and placement checklist every time we've made a measurement, we never shorted anything out, opened anything up, or operated outside the measurable range of the meter in either voltmeter or ammeter mode. I'm hoping this proves something I've been saying all along. Imagine how well lab will go if you know what you're doing. Your first lab may not go as well as this. And I'll admit, I do dumb things every once in a while, like trying to take current measurements with the power off, or writing 1, 2, 3 when I'm in 3, 2, 1, or just punching wrong numbers or wrong operators into my calculator. Every time I made an observation, though, I check my expectations prior to moving on to the next step. That's the point of this experiment. Compare the theory with reality. If at any time I noticed an extreme deviation between the two, I would have immediately stopped and rectified the situation before continuing. Imagine if I had a 47 ohm resistor, a 47 kilo ohm resistor instead of a 470 ohm resistor because of an errant reading of the third band inside the 4-band color code. In either case, my current would have been a power of 10 different. This is a cause for immediate concern. Be sufficiently aware enough to recognize this event and shut her down till you fix it. Alright, break is over. Now, take your observed voltages and your observed currents and multiply them together to determine the observed power dissipation at each operating condition. That's this column in our empty data sheet. Compare your observed power values with what you'd expect. You should be looking good. Let's move on to our second resistor. Our second resistor is 390 ohms. What's the 4-band color code for a 390 ohm resistor? A 3 is orange, a 9 is white, and it's followed by 1 0, so that's brown. And let's use a plus or minus 5% resistor with a gold 4th band. So our resistor is orange, white, brown, gold. Go fetch. Our DMM in ohm meter mode says this guy is actually a 390.1 ohm resistor. This is so close to 390 ohms, I'm going to put it in a nerd museum when we're done with this experiment. Let's just speed walk through this series of measurements because it's more of the same. What we're going to do is apply close to 0 volts, 2 volts, 4 volts, 6 volts, 8 volts, 10 volts, and 12 volts to this resistor and measure and record the current every single time. Then we're going to take our observations and compare them with our expectations. Even your lab partner could do this. At 0 volts, we'd obviously observe 0 milliamperes of current and would obviously dissipate 0 watts of power. Remember, you're filling out your data sheet as you go along. At close to 2.092 volts, we're observing roughly 5.208 milliamperes of current. Compared to our expected value, we're off to a good start. At close to 4.022 volts, we're observing roughly 10.018 milliamperes of current. Looking good. At close to 6.099 volts, we're observing roughly 14.975 milliamperes of current. Looking good. At close to 8.063 volts, we're observing roughly 20.56 milliamperes of current. Looking good. At close to 10.07 volts, we're observing roughly 25.83 milliamperes of current. Looking good. Finally, at close to 12.01 volts, we're observing roughly 30.98 milliamperes of current. Just because I'm crazy, I'm measuring current at the downstream end of the resistor before it returns to the negative terminal of my power supply. Again, this shows you can measure current anywhere inside a path, and you should get that same value. Now take your observed voltages and your observed currents and multiply them together to determine the observed power dissipation at each operating condition. If you compare your observed power with the expected power, you should be looking good. All right, we got all the data we need to wrap this up. Should we take a break? No, we should not. We should wrap it up. Don't be in such a hurry to leave a lab environment. Yes, we might have all our data, but let's finish it while we're in the lab. What's the rush? Are you hurrying home to play some stupid video game with your imaginary girlfriend? Finish your lab. You might have missed some observations or entered faulty data. This is the time to discover it, not the night before the lab is due. The only task remaining us is 2 graphs. We need to plot our observed current as a function of our observed voltage, and we need to plot our observed power as a function of observed voltage, and then use these 2 graphs to verify our earlier hypotheses. At this point, you should have 2 data sheets, expected and observed. Notice I've reformatted our expected data sheet to use units of milliamperes and milliwatts rounded to the 10th place to make it a little bit easier to read. Just grab some random values and make sure we're tracking. At 4 volts, we'd expect a 470 ohm resistor to draw 8.5 milliamperes of current, and it did draw 8.4 milliamperes of current. At 6 volts, we'd expect a 390 ohm resistor to draw 15.4 milliamperes of current, and we observed 15. There are some slight inaccuracies, but as a whole, Our hypotheses seem to be verified. For a given voltage, let's say around 4 volts, the smaller resistor has higher current, and the larger resistor has less current. For each resistor, as we increase applied voltage, current increases. And additionally, as both voltage and current increase, power dissipation appears to increase in a nonlinear or geometric fashion. We need to plot current as a function of voltage. We need to plot power as a function of voltage, and then use these two graphs to verify these hypotheses. See if you can enter the data in Microsoft Excel and use a scatter plot to make a graph. This lab activity assumes you're familiar with entering data and making scatter plots in Microsoft Excel, or can at least get Clippy to do this for you. Speaking of Clippy, where's my sandwich at? Clippy did not have my sandwich, but he did give me these two graphs. Pause the lecture and see if we can perform an analysis of these two graphs. What properties do these graphs illustrate with respect to Ohm's law and power dissipation? How do these graphs visually demonstrate our hypotheses? Number 1, that at a given voltage, a larger resistor will have smaller current, and a smaller resistor will have larger current. Number 2, for increasing voltage, a given resistor will experience more current. And number 3, that power is a nonlinear property. Number 1, the graph of current as a function of voltage clearly shows that at the same operating voltage, let's say right there, the 390 ohm resistor, which is red, has this current, somewhere just below 20 milliamperes. However, at the same operating condition, the 470 ohm resistor would experience just above 15 milliamperes of current. Again, when voltage is constant and resistance goes down, current goes up. When resistance goes up, current goes down. Property 2. Additionally, this same graph shows that both resistors behave linearly in that for every increase in voltage, there's a proportionate increase in observed current. As voltage goes up, current goes up. The smaller resistor, the 390 ohm resistor, has a steeper slope. The larger resistor, the 470 ohm resistor, has a shallower slope. In this case, it's illustrating a case where resistance is kept constant, and for every increase in voltage, there is a proportionate increase in current. Property 3. Finally, our second graph shows that power is not linear. It's behaving geometrically like a rocket ship. This is an important consideration regarding component performance and specifications. For every doubling of voltage, power dissipated will quadruple. What'd you think of this activity? Did you learn something? Could you do this on your own? If you've been actively involved in watching this playlist in its intended sequence, I think you could. Get in a lab and put these skills to practice. If you don't have a lab, get yourself a good DMM, power supply, and a couple resistors, and try this exact same experiment by yourself. Stay safe. All right, we are officially done with this lecture. But quick show of hands, who wants to see me set something on fire again? Okay, everybody's in agreement. Here we go. Here's two resistors with the following 4-band color codes: yellow, purple, gold, gold, green, brown, gold, gold. The first one is a 4, followed by a 7, and multiplied by a 0.1, or 4.7 ohms. The second one is a 5, followed by a 1, and multiplied by a 0.1, or 5.1. Let's have a race. Who's going to go up and smoke first? Quick hint. What does physical size indicate about a resistor? We're going to use a power supply that maxes out at roughly 571 milliamperes of current. Ready, set, go. Both of them are drawing the maximum current. All right, smoke curling off the 5.1, 4 seconds into the game. 4.7 still holding. Smoke alarm is going off. Hopefully it isn't hooked into the sprinkler system. Probably should have checked that before I did this. Whoa, we got a bright flash on the 5.1 and current suddenly ceases. It melted in half and opened like a switch, cutting off all current flow. Super cool. 4.7 still holding. Still holding. Alright, I grow tired of this game. Yep, super hot, but still standing. 4.7 is the champ. Did you back the winner? The dead giveaway is the physical size of the two resistors. Yes, I know 4.7 ohms is smaller than 5.1 ohms, but it's clearly a physically larger resistor and obviously has a larger power dissipation rating. These two resistors have relatively close resistance values, but have totally different power ratings as indicated by their physical size. A 5.1 ohm resistor drawing 571 milliamperes of current was dissipating roughly 1.7 watts of power, and a 4.7 ohm resistor with 571 milliamperes of current going through it was dissipating approximately 1.5 watts of power. The only reason the 5.1 ohm resistor folded early was primarily because of its smaller physical dimensions and power handling ability. That was super fun. Now about that fire alarm. Before we say goodbye, let's take a moment to let it all soak in. After all has been said and done, I want you to reflect upon what you've seen today. We applied everything. We used a DMM in ohm meter mode, voltmeter mode, and ammeter mode. We used a power supply. We built circuits on a protoboard using fixed and variable resistors. We used the resistor color code. We used Ohm's Law and the power equations. We calculated, observed, recorded, measured, fiddled, adjusted, troubleshot, graphed, predicted, and compared expected values with observed reality. We did it all. We even set a couple things on fire. For educational purposes, of course. It has been a long road getting here, but realize this is just the first step. More enlightenment awaits, but it is all based upon what we did today. You simply cannot proceed without a solid understanding of Ohm's Law. We demonstrated and proved today this concept is observable, useful, and most importantly, true. I want you to put your hand on top of the internet and repeat after me. I believe. I believe in Ohm's Law. I believe I can use my knowledge of Ohm's Law to predict electrical properties and troubleshoot electrical circuits. I believe if I showed up prepared and know what I'm doing, lab will go well and I will learn something I can apply in the future. In conclusion, this activity verified Ohm's Law using real-world components and instrumentation. We discussed common troubleshooting scenarios for basic circuits, and we graphed current and power as a function of applied voltage for two different fixed resistors. We also got an opportunity to see some things go up in smoke. Remember to review these concepts and practice these techniques as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.